Hello everybody, welcome to our second video on exact differential equations. And in this video we're going to be talking about how can we tell ahead of time whether or not a differential equation is exact. So we don't have to go through the brute force of trying to solve it and figure out the hard way. Alright, so let's go down and take a look. What we were looking at when we were looking at exact differential equations is we were looking at differential equations of the form as follows. The wolves are howling outside. I don't know if you can hear that. The differential equations look like this. All right. Now, if it is exact, that means it came from a function. A function f of xy equals a constant. And how does this unfold to become this? Well, we differentiate both sides, right? And we end up with the following thing. The derivative of a constant is 0, so I got 0 on the right-hand side. So this is going to have this as a solution if we can match up m with fx and n with fy. And we went through how to find f in the previous video. So, but what I want to do is I want to point out one other thing. So we know from Calc 3, from multivariable calculus, we know something called Clairaut's theorem. Clairaut's theorem says that if a function has continuous partial derivatives, so if fx and fy are continuous. Oh, I'm just popping in here just briefly just to point out I made a slight little goof here. We need the partial derivatives, the second partial, oops, oh boy, I'm messing it up again. Second partial derivatives to be continuous, okay, not just the first partial derivatives. Then that implies that fxy equals fyx. Those have to be the same. So we can make use of this theorem here, okay? You see, if m is really fx and n is really fy, then if I differentiate m with respect to y, right, my is going to be fxy. And if I differentiate n with respect to x, then that is fyx. But Clairaut's theorem says that if these things are continuous, in other words, m and n are continuous, then these things have to be equal. And that tells us that my has to equal nx. And so that necessarily has to be true in order for the differential equation to be exact. And so that's a quick check of exactness. What we'll do is we'll check my and nx and make sure that they're equal. If they're not equal, then it's hopeless. But if they are equal, then there is hope that we can check this. All right. So let me show you an example here. So we'll do this differential equation. So let me just also specify if these things are equal. Well, we haven't learned this yet. I was going to say this implies exactness, but I will write it. It's necessary that this be true if the differential equation is exact, but we haven't yet argued that if this is true, then the differential equation is exact. But it turns out that is a true statement. We argued this direction, that if it's exact, these have to hold, but it also is also true the other direction. All right. So I'll put a little star here because we'll talk about why that's true in a second. Okay. But let's look at an example here. So okay, we have this differential equation. And I want to know, is this exact? All right. So what I'm going to do is I'm going to check the derivative of m with respect to y, so this is m, and I'm going to check the derivative of n with respect to x and make sure that they're equal. Okay, so let's differentiate this with respect to y. Treating x as a constant, right? What do we get? We get 2y. Pretty simple. And now I'm going to differentiate this with respect to x. Well, when I do that, I get 2y. Are they equal? They sure are. And therefore, I know this differential equation is exact. Right? So I can go through and try to find the solution. Okay, let's look at another example. This is an example from our last video. Okay. What I think, you know, I don't have it written down, but I think it was this. Y plus 1 dx plus 2x dy equals 0. Is this exact? All right. Well, what I have to do is I have to check the derivative with respect to y of this guy. And I have to check the derivative with respect to x of this guy. Well, the derivative with respect to y of this one is 1, and the derivative with respect to x of this one is 2. Are they equal? Nope. So it's not exact. Which is what we concluded in the last video, but it took us a bit longer. This is a super quick way to do it. If these are not equal, can't be exact. Now, what we haven't talked about yet is how do we really know that if these are equal, then it is exact? We know that if they're not equal, it can't be exact. But how do we know that they are equal, that it is exact? Now, I'm not going to go through the proof of this with you, but I am going to point out that in our book, oh, where are you, book? You're on the green screen. That was me looking up Clairaut's theorem. Actually, while I'm here, let's point that out. There's Clairaut's theorem from a calculus textbook. So that's what I was talking about. Okay? But let's go back to the differential equations textbook that we're using. And here's the theorem that I'm talking about. It's theorem 2.5.2. Right? And this is exactly what we were saying. If m and n are continuous, and they have continuous partial derivatives, then this is exact if and only if we have this equality. And this is exactly the equality that we're checking. All right? And this is if and only if. So that's the both directionality that I was talking about. If and only if means it works both ways. All right? So that is a useful theorem that we can just quickly check to see if our differential equations are exact. And that's all I have for you in this video, and I'll see you in the next one.